discussion section. So let me start with a question and answer. I think that I see, I'm sorry, because now they have been changing since the last time that I looked. So I will go in the order in which I see them in the question and answer. I see also rise end, so now I'm confused of what should they give the priority to. So let me try to go for the question and answer, and then I will go for the rise ends, okay? Unfortunately, the person that made the first question in the question and answer, I think has left. Yes, so let's see if we can find the second one. Harry, you can make the question. Harry, you can talk.
So I want to ask under which circumstance these jets can be triggered, and that can be similar in stellar black holes accretion also.
I think this is a question for Luciano, if I understand correct.
Yeah, so actually this is a very good question, and the answer is we don't know. Jets are ubiquitous in astrophysics. You see them in stellar mass system, in X-ray binaries, and you see them in AGNs, and you see them in gamma ray burst, and of course, topologically they're all the same. It's a plasma of highly energetic particles leaving a black hole. But what produces the energy powering these jets could be different mechanisms, could be the same mechanism. If you are involving a black hole into this, then there is the suggestion that this could be a Blandfors-Dirac mechanism, an interaction, essentially a Penrose process associated with the presence of a magnetic field entering into an ergosphere. Whether this is really what powers AGNs and gamma ray bursts is unclear. Another possibility is that actually the energy is coming from the disk in terms of centrifugal powering from the matter simpling falling into the black hole. These two models of powering have different predictions, different consequences, but right now we don't have any evidence that favors one over the other. So when we do our simulation, you may ask, what is it that you are actually doing? What is it powering these jets? That is also unclear because we don't. The models behind this are rather simplified, and we have with very simple field topologies, and we have much more complex physics going on. So it's not clear that whether it's one or the other, maybe both playing a role into this. Right now, there are studies which are trying to assess which of these two modes is the predominant one. Blandfors-Dirac seems to be very appealing, in which case then you would need to have a rapidly rotating black hole in order to produce these very energetic jets. And as I was saying before, we don't have evidence or clear evidence that there is that we can measure spin from M87. But if you put in other information, in particular, a recent paper that is going to come out in a couple of weeks, we haven't published this because it is still embargoed, seems to indicate that in the case of M87, given the jet topology and the energy in the power spectral density, then you need to have a rapidly rotating black hole, in which case Blandfors-Dirac would be a very natural explanation. I don't know if I answered your question.
Yeah, sir.
Okay, thank you.
Great. So the next question, there were some extra questions from Deepak Vaid concerning the talk of Silke. So I don't know if you want.
Sure. I mean, I've written them, but I can ask them.
Well, I've seen that you had many in list, and I told you that you could do some others after.
So
Right.
just the two things. So the first one, okay, so is an analog of the black hole mass in this situation? Would it perhaps depend on the size of the drain? The black hole, so you can locate the horizon, and then so the way it is, you have to calculate the acceleration on the fluid flow at the event horizon, at the analog horizon. This is a fair way to say it in a quick way. So you can associate, you can calculate the surface gravity associated to your analog space-time. And then if you want to, you can then through this way define an effective mass. But this is not something, it doesn't have the same meaning. It's just you can calculate the surface gravity. In this sense, you can think of a mass, of an effective mass. But that's just the definition. It's not the size of the drain. It is really, it has to do with the fluid flow, how the radial component of your fluid flow. And of course, if you have a bigger drain, you can drain size, you can speed up the radial velocity field. So it's not that simple, but yeah, you can play with the drain size. And then
Yeah.
Sorry, there was some internet problem. No,
Okay.
you mentioned during the talk that the water height is plays the role of the mass.
No, I mean, if I have a system with a certain square footage, I have a certain area, and the water height is the total mass of the system. The analog gravity system, the mass in the upper basin is the mass of fluid inside. And so when you drain the height, yeah. So, and if you change the height of the fluid flow, then the total mass of that water is changing in this sense. I wasn't talking about the effective black hole mass or so. But when you do this, the effective surface gravity, the horizon, everything changes. So also your effective mass would change.
Okay. Maybe we can go now to the people that raise the hand. So I have in the list Charlie Robson. You're allowed to talk.
Hello. I also have a question for Dr. Weinfurtner. So I was wondering, does your analog of a black hole, so does the hydrodynamical analog stretch so far that you can assign an entropy to your hydrodynamical black hole? And if so, in terms of the parameters of your system, and if so, how would you interpret that entropy?
So I think there are some people who have maybe thought more about it, Stefano, Luis, and Matt, and so on. So not straightforward. I think people are looking into this. I don't know, Stefano, what is the best one can say?
Well, if I should say something about the entropy of an acoustic black hole, I think that for sure you can define an entanglement entropy, given that you have phonons, you have an horizon, you can define an entanglement entropy, and there's a natural cutoff due to the modified dispersion relation. You don't need an artificial cutoff as usually you need in order to have a finite result for your entanglement entropy. And I would say that it would be naturally proportional to the area.
I see. So the entanglement entropy could be associated to the entropy of the hole itself.
Yeah, another thought that is if it fits in a first law, something like that. That would be the interesting things to see, because normally we derive that resting on the Eisenfield equation, that here they do not. Seems too old. On the other side, back reaction, because I had a question myself for Silke, maybe I can connect to this, Silke. Because on the other side, you find that back reaction, and I must say also in another independent work, we find a back reaction, in particular Hawking radiation, seems to work remarkably similar to the standard back reaction in black hole physics, but it's based on queer equations which are not the Eisenfield equation. So is this just a coincidence, or there is something subtle about it that we are missing? Can there be a deep reason for that?
I mean, so first of all, in general, back reaction is related to conservation laws, right? So is that things can not just disappear. So the mass of a black hole has to shrink because there is the Hawking radiation is carrying away this mass. It's a bit super simplified said, but in a way, angular momentum and mass in the analog system, they also have some conservation laws, which when you derive them from the overall dynamics, you can perhaps simplify them to some level. So I have to be honest, it's a question, how much alike can you make them? And what do you mean with being alike? I think that there could be a step towards this is to just understand how Hawking radiation or quantum processes change when you have a back action in a system. So when modes couple to the zero mode in the system to the background, what are the sort of observational consequences, and can you actually measure that? So this would then help you to guide a way to calculate this back reaction and treat it and see if your modeling works in the analogs. So I think even if it's not exactly black hole, it's still a really valuable area of physics or in these analogs to investigate, to understand those processes. And one thing in the analogs, which is always nice, you can make the effects large. So once you understand how back reaction is happening, you can try to enhance it. And so you can say, well, maybe going from a regime where back reaction is present but small, maybe you can make it large. And one thing is always interesting is, what's the validity of this back reaction effects for how long, and how does it imprint in all the scattering process and so on, and can you actually extract this experimentally? And I think that's an interesting challenge.
Thanks. So we have 3 raised hands. The first one, I see in my order, is Samik Mitra. Then there is Sarah Sagafi, sorry. And then there is a question by Shinji. So let's go for Samik Mitra. You are allowed to talk. Samik, can you hear me? Can you?
Yes. Am I audible now?
Yeah, you can speak.
Okay. So I have a question for Professor Rezzolla. So the first question is, like in GRMSD simulations, in most of the papers that I have seen, that the spin values, the black hole spin value that has been chosen is around 0.9375. Is there any specific reason for that? I mean, or whether, why this is a preferable choice?
Luciano, you are muted.
Yeah, sorry. No, there is no deep reason. It's just that, we were scanning the space of parameters and setting spin into quantum numbers of 1/16. And I think 9.93 is just 15/16.
Yes, yes. Okay. And so regarding the simulations, there are 2 kinds of model for GRMSD. Mainly people are following this Fishbone-Moncrief torus model, or recently some of the simulations are from this thin disk model. So we have seen that the most acceptable models are these thick disk models. So what kind of differences we will expect for these 2 kinds of model?
So I think anything suggesting thin disk should be treated with a certain skepticism. These are extremely hot disks, and you would expect temperatures such that you cannot have a thin disk. Essentially, you have a thin disk when the plasma is efficient enough in cooling and therefore decreasing its pressure and its height. Given the present knowledge of what's going on, this cannot happen. That's why all of our disks are thick. But don't be fooled. The fact that we have a thick disk doesn't mean that if you go close to a black hole, you have a very nice self-contained disk. These are just providers of matter, and it is very much possible that these disks are, as they appear in our simulation, just very close to the black hole. But as you move further out, they may become different. They may even not be axisymmetric, because they may be fed by streams of matter coming from the stellar environment further away from the black hole. So, I think having in the order of a few hundred Schwarzschild radii, a thick disk, which accretion is driven by an MRI, is a reasonable approximation, but further out things may be and look very different. This is something we are exploring now, and if you want to know why we are exploring this, is that it's clear that you need longer and longer simulations so that you have a steady state which is as robust and stationary as possible. But of course, if you start with a self-contained torus, the torus will run out of matter. You will have accreted matter if you run over very long time scales. And so you need a way of feeding in material. And that's why we are considering either very large tori to start with, or ways in which we can provide material at the other edge of our simulations.
Actually, sir, I mean,
okay, maybe now we can.
Sir, just one follow-up comment. I mean, for this torus model, all the simulations that we have seen, that I have seen all these papers, that it doesn't contain that Blandford pane outflow. So, but for the thin disk model, we can get that. I mean, is there anything related to that? I mean, is it correct?
So as I said, we don't know if the Blandford pane is working, is actually at action. When Blandford pane is providing you a disk wind and then some powering of the jets through this disk wind. We do have a disk wind. It's just not the way, in the simple semi-analytic model of Blandford pane. So you have to appreciate that, when you start with a simple analytical model, you have some predictions, and these predictions are probably contained in your simulations in some shape or form, but your simulations are exploring highly turbulent, nonlinear regimes, and it's difficult to extract exactly that signature. So right now, we think that there is both Blandford pane and Blandford-Naik working in our simulations, and then it's going to be the actual observation which will tell you, which of the two is the predominant one.
Okay, thank you.
Okay, so the next question is for Sara Sagafi. You can talk. Oh, sorry.
Okay. Hello, everyone.
Okay. Yes. Yes.
Can you hear me?
Yes, please.
Okay. Hello, everyone. Professor Rezzolla, I want to ask a question. Using from imaging supermassive black holes, is it possible to understand how they have been formed? I mean, the process of their formation.
I'm afraid not. You're looking at something which is pretty old in terms of formation. These objects were produced cosmologically, and now they've been accreting for billions of years. Can you hear me?
Yes, yes.
Okay, so what you may hope is, if you really are interested in Genesis, is hoping to see many of these imaging many black holes, and then maybe if you image many black holes, you can think of doing statistics and from there learn. However, when you do your back of the envelope estimates of how many candidates you have that you can image, I mean, supermassive black hole that you can image, you need just one hand. So, it's very difficult to make statistics with just a few sources. That's because, as I was mentioning in my first slide, you need to find the right combination of mass and distance. We have bigger black holes than the one we've seen, but they are further out. We have smaller black holes and they're further in. So once you look at the right size on the sky, you have Sagittarius A star, you have M87, you have NGC 379, and a couple more. But the first two are really the best ones.
Okay, thanks. Thanks.
Okay, so now we have Shinji Mukoyama. Shinji, you can unmute. Thank you.
Thank you. So I have a question to Silke and Stefano, actually. So that you mentioned that in the context of analog gravity, you mentioned the back reaction and also first law. So that I'm wondering if you can define a kind of analog Einstein equation or not.
Well, I can only tell you what we did, and I don't know, Silke probably can refine on what we did was to look at the Hawking radiation in a canonical acoustic black hole and take into account the back reaction of the Hawking phonons on the background using the background equation that describe exactly the coupling between the phonons and the background geometry of the flow. That would be the analog of the Einstein equation, and we find out that the acoustic black hole shrinks as it evaporates.
That's very interesting. I see. So can you also do kind of emergent gravity or something like that?
Sorry, can we? Well, it is the
emergent
problem
gravity.
with emergent. Yeah, but what we found is that if you have a non-relativistic BC, you can recast the equation for the background as a Poisson equation, which has, however, a massive graviton with a typical wavelength, which is order of the Hill length. So that is basically a Poisson equation, which is nabla squared minus 1 over L squared applied to the gravitational potential that you can define from the acoustic geometry. And that is equal to the to a proportionality factor depending on macroscopic constant, which is G Newton, is playing the role of G Newton, times the density of the phonons, plus a cosmological constant, which is negative in this system, which is by default a negative cosmological constant. So if you go to a relativistic BC, you can get to Nostrom gravity. If you fine tune the system in such a way that the speed of sound is the same basically as the speed of light, so it's a kind of unphysical corner, but basically there you can get Nostrom gravity, which is as you know, a scalar theory of gravity, which is consistent. So I don't know, Silke, what if you want to give your part of the answer to the question by Shinji?
Well, the thing that always puzzles me a bit is if you say, okay, I want a system. I mean, you would like a system that has a dynamical equation for a spin 2 particle. And so in these analogs, we have, scalar modes. And there was a long time ago, I don't know if Stefan or Matt remember, there were these quantum rotor models where he set up a complicated model and said you could get a spin 2 excitation as well. But what is really, it's sort of like, when can this thing be right in the kinds of the ingredients, the propagating degrees of freedoms? And one of the things for these models was that, okay, he got the spin 2 excitation. It was a bit of an artificial construct, but still he has a spin 2 excitation, he has a spin 1 and the spin 0 modes. And he was basically then arguing how you could, because you get all the excitations, that's the special thing about gravity, that you only have the spin 2 excitation. So then if you had, suppose you could find a model which has a spin 2 excitation and you have some effective equation for this mode, which might be linearized GR or something reminiscent, you would have the problem with all the other propagating degrees of freedom that they shouldn't be in there. What is the argument? So I think it would be beyond what Stefan already said. Could you extend the class of analogs? And could you construct something with spin 2 degrees of excitation? Matt is shaking his head. No.
The problem is background independence. It's very difficult because you need to get back the background independence. Even Nostrom gravity, you have a fixed structure, which is the causal structure of Minkowski. Every metric is conformally flat. So the background independence is very difficult to get in a system like an analog system.
Yeah, I mean,
apparently the only way you can, is by a different notion of locality. There is a theorem by Don Marolf, that shows that this kind of emergence requires that there is a different notion of microcausality, if you like, what you call kinematic non-locality. Basically, a different notion of what commutes a space-like distance between the microphysics and the macrophysics. So that seems to suggest that emergence, analog gravity, requires some sort of different notion of locality between the fundamental system and the emergent one.
I see. Yeah. Thank you very much. Very interesting.
Well, and now I think there is Luciano.
Yeah, so I also have a question for Silke. I mean, I'm a bit baffled still about the back reaction, but the question is, all of these vortex experiments that you are, we're working in in a gravitational field which is static or stationary. So is there a way in which you can change this by, producing an acceleration either in free fall or even, larger than g? And would you expect to see some changes because of this?
So, okay, so there are two things. We are playing in one system with, so when you change, if you work with surface waves and you change G, free fall, we are actually doing something like that, or planning where we put a two fluid system into a strong gradient magnetic field, and you can even change the sign of gravity because of the diamagnetic properties of fluids. So when you do this, you get a cosmological space-time geometry. You can change the propagation speed in these systems. You can even make them from hyperbolic to elliptic. What you can, if you want to have a time-dependent rotating black hole, it's easy to do, because all make it stationary is hard. Make it non-stationary is not hard. For example, one of the things we're doing and analyzing right now is we are looking just as water draining. And so we are completely taking it out of the equilibrium. And what we notice that the light rings are still there, but we need to find a good background description to match what we are seeing. So it's not difficult to make it, to put some strong time dependence in there. Right? And it seems to me, and this perhaps it's reasonable anyway, if the time dependence is not, if it's a little bit of time dependence, we all thought, okay, depending on what signatures you're looking for, if the frequencies are much higher than the change rate or so, we should see. But I also find that it seems to me that it is a bit stronger. It seems to me that it's almost like you want to break this effective field theory with a curved space-time description, and you hit it and somehow it is persistent. I've seen a lot of things recently. We start to wonder, how robust these effects are. So I think that's the great value of these experiments as well, to explore where the techniques, the methods we're using, we're expecting them to break down.
Mm-hmm. Okay.
And for example, to say, one of the things which I'm really keen on looking at, and we never get around, is I want to break this axis symmetry in the fluid flow, and then the wave equation not separable anymore. And then how will ring down look like? We can just look and see what's still there, and then we need to find a model to match what we see. That's the advantage. When we make a model, we can directly rule it out in a way. That's a nice thing. And of course, you're doing the same thing with numerics, right? You have some analytics models and then you compare it to numerics. But in a way, also, you can set up some weird stuff and see if how much your insights change.
Yeah, of course. Yeah.
Okay, so now we have a question from Germain Rousseau, and then we are going to close, but I would like to close with a question for Samaya, and I have also a fast question for Luciano and Silke. So I give the possibility to speak to Germain. Please ask your question. Germain, can you hear me? Because I see you're still muted, but you are permitted to talk. Otherwise, we can read the question. It's in the question and answer. For some reason, he cannot talk. So you see, Silke, should I read it, or you can read it in the question and answer? Are you sure that the variation of the mean water level is not due to a nonlinear effect known as in fluid mechanics as wave set down, which depends on the amplitude square of the incoming water waves before the interaction with the vortex? I stopped with the first question, then there is other. Okay,
I mean, it's a nonlinear effect. It scales with the amplitude squared. I'm not sure what Germain is asking. He would need to classify. I mean, if you have waves propagating on a non-homogeneous background, they can adiabatically changing, but this is not. So this would, I'm kind of don't understand what it means before they interact with the vortex. I don't understand that part of the question. Maybe Germain could classify.
Yeah, because you see in the second part it says this is why one usually sends tiny amplitudes in the other analog experiments, typically 3 microns. What are the amplitudes used
okay, thank you.
in your back reaction?
No, I get it. No, it's not. The back reaction effect is not different modes are interacting. The back reaction effect, the mode interacting with the background. It's not mode interaction. It is mode background. It is that interaction. It is really a change of the background, not mode interaction, which are non-linearities. Other than, you know, we also can see this.
Okay.
I mean, yeah, it's possible to do this as well. And then the smaller the amplitude is, but we are in the linear regime. And this is happening in the linear regime. This makes no sense. The amplitudes are small enough that in fact, the whole perturbation, I'll give up. I can't explain it better, but now it's with the background, 100% sure.
Okay, so I think that we can round up, but I will use my privilege as chairman to satisfy my curiosity. So I have a question for Samaya, which is, I think a kind of, a straight question is the following. We have seen that there are events where neutron stars merge and they go in the range, the byproduct you showed were in the range 2 to 5 solar masses, right? And my question is, are we imagining that this is some new object? It's a new category, which is intermediate between a neutron star and a black hole. Are we equipped with current searches to detect, to distinguish the fact that that is not a black hole? Imagine there is something like a strange star, something, you see what I mean is that
it's an yeah. No, in terms of exotic compact objects, yes, would we be able to say something? So yes, I didn't go in depth here in the talk, but essentially there's a parameter, this tidal deformability parameter, which essentially gives you the ratio of the induced mass quadrupole against the external tidal field of an object with a companion, essentially. And here there have been proposals. And so one of the things we were able to do with GW170817, because it was such a loud signal, but it was still, we missed quite a bit of the final orbits just before it merged because we didn't have the sensitivity at the high frequency end of the band, but we could get constraints on this tidal deformability. And what the hope is that we'll be able to actually say something with, as the detectors are now improving in sensitivity at this high frequency end of 1.5 to 2 kilohertz or so, we will be able to catch more information essentially as the size of the object becomes comparable basically to the orbital separation. That's when you really accumulate this 5 post-Newtonian effect of the tidal deformability. And there have been proposals to measure this, for instance, for different kind of boson stars, etc. And so there are several papers I'm happy to send or put on the Slack that
this is very...
have proposed this, yes. And so that, I think that's the aim we're trying to go to, yes. And exactly also other numerical relativity simulations have looked in terms of looking at more exotic or boson stars, etc., merging, and whether their counterparts or signatures may be different. So there is work going in that direction, but I think because at the moment we haven't reached that sensitivity yet, as well as there's a lot more work to be done in terms of the theory, in terms of forward modeling, if that makes sense. Yes. To understand that, but yeah, the tidal deformability, for instance, for black holes is 0, or for isolated black holes, and so this is a parameter that is kind of key, not just for neutron stars, but also for other exotic compact object constraints. Thank you. And I
just have a comment to that.
Yeah, sorry. Yes, go ahead.
I just have a comment on that. There is one of the poster of this conference, which is reporting a work by Cecilia Chirenti and other people that now one is Posada, the person that was presenting the poster, that they found that if you have an ultra compact object, as the compactness goes toward the one of the black hole, the log number goes to 0 smoothly. So that would also be if you have you are considering ultra compact object, having a constraint on the deformability could translate in a constraint on data compactness. That would be very interesting. As just a comment.
Yeah, no, thank you very much for highlighting it. I will look out for it. Thank you.
Then I have a question for Luciano, which is a fast question, which is it possible, I mean, probably it's a stupid question. Have you thought of the possibility to have an experiment in space to increase the baseline? I mean, or is technically unfeasible at the moment? Let's not talk about models.
It's not a silly question. You know, we have the planet we have, and we can't get it any larger. So if you want to have a larger baseline and so higher resolution, you have to go to space. And there you have, you know, a variety of options. Either you have a radio telescope on Earth and a satellite, or you have a series of satellites. And we've actually written a paper on this where we show that with a rather modest mission, with 3 satellites with a rather low orbit, you know, you can have them in a triangular shape with a continuously varying baseline between them, and then the visibility space, this space, you know, that I showed you at the beginning, where you have, which is just poorly populated at the moment, would be filled completely in around 6 months' time. And then all of a sudden, you know, your resolution would go up over factor 10 or more. And all of these questions about alternative black holes, then alternative black holes in alternative theories or alternative compact object, they can be addressed. So yeah, we need to go to space in order to really test gravity. Right now, I think we can only make consistency statements.
Checks, you're right. Very nice. My final question is for Silke, and concerning the ring down. Have you considered what happens if you make your configuration slightly subcritical? So, you know, for example, Hawking radiation in acoustic black hole, there is these subtle things that even if the configuration is slightly subcritical, you don't have an horizon, still you do have some excitation of the phonons. So because of the modified dispersion relation, if you like. But here in the ring down, I was wondering if you have tried to go slightly subcritical, so remove the horizon and see how much it does change. How much is important, because the horizon is providing a different boundary condition, of course, right?
Yeah, that would show itself in the exponential part. So in fact, the simulation for the quantum fluid has no horizon, it's just rotating. So because we're looking for something that only depends on the light ring, but not on the boundary conditions, this to get a nice, where you would see the boundary condition play a big role, is I would expect it, I mean, there are experts, a lot of people know it better than me, but I would expect that the exponential decay is the one thing which would be highly influenced by this. But the light rings, what we see in the experiments, just to the accuracy we can measure it, the real part does not depend on the boundary conditions. I have to say,
great.
To the one thing I always have to say, we have an agreement, we have dots and an error bar, and our error bars are large enough to hit that theory prediction, okay? So, and as I said, if you want to do high precision measurements, which we started now, where we go down to nanometers measuring this, we do hundreds of repetitions, and we really test the effective field theory. I cannot do this in such a big system. I can't control a system to repeat experiments to the precision needed to make it worse to look that closely. No large experiment can be controlled so much, I think. So I think we need to go to small systems and quantum fluids to address this sort of questions.
I see. Okay, thank you. Okay, I think that more or less the time is up. I think it, at least for me, it was ultra interesting, both the talks, which were great, and thanks again the speaker, as well as the question time. So I don't know if the